Good morning. Okay, shall we start? Zafira-san, can you start first? I cannot hear your voice.
Hello?
Okay.
Okay.
Yeah.
So I was thinking what to proceed for the next research topic or continue from the current study.
Hmm.
So I was thinking like because I'm doing 10 story and Sarah's doing for 15 story, and I will continue for high rush within 20 story. And then from this increased number of story, we can try to optimize the damper design and also the design procedure. So I haven't finished study these two paper, but I can just like let you know what this is all about. So this researcher Iman Haj Rusliha, like he studied about optimizing the design performance. So one first using viscose damper in the steel frame. So basically this the one what he did is the let's see objective is to use for retrofitting. So for example, if we have a steel frame, current steel frame structure, and there's a possible like bigger earthquake in the future, so he want to retrofit the building with viscose damper in the middle of the story. So this is the chapter inside inside the paper. So chapter 2 explaining about the structure itself. It's using Eurocode. And then the energy dissipation device was viscoelastic, a viscose damper. And chapter 3 is discuss about the performance-based optimization for code-based design spectrum. So there's a few method that he used to optimize the design. One is to use mean earthquake. So he chose a several type of earthquake, and then he tried to optimize the earthquake to match with the code spectrum. So he used EC8 spectrums. And from this all earthquake, he tried to find the mean value for the time history analysis for the building. And other method that he used is to using uniform damage distribution. So in order to achieve uniform damage distribution, he optimized the damping coefficient by using this formula. So basically, this is CNDI is means for the current damping coefficient at that interstory building, and then times the maximum interstory drift divided by the target story drift. So for example, in our building, the target story drift is 1.28 centimeter. So if you want to get the new coefficient damping, we can use this formula. And then it also about talking about the effect inertial damping distribution, and it also have the interaction, which I haven't really understand about interaction and conversion effects. I need more info like knowledge about interactions, how they do conversion and interaction in the design procedure. And in next chapter, it also talking about the sensitivity to select a earthquake record. Yeah, and chapter 4 is optimizing solution under natural record, and he used this the local and global damage index. In Seratd, we is automatically calculate the damage index from the data output. But here is also it used this formula to calculate the damage index. Yeah, and I haven't finished study the others chapter. And then there's another paper under him also. But this one is in the RC frame with the friction wall damper. So the friction damper in the middle is mm, it's not the same as our structure, but our structure use beam as a location of the damper, but this paper used the wall as the energy distribution device. And in the design, this paper also have a little bit similar compared to the first one, this one. So in this paper, first they have the building itself and then the energy distribution device. And then first, in this paper, because they use wall and friction damper, so it use slip load range, means the horizontal load displacement. And then the proposed performance and optimized methodology, it use optimizing the design for selected natural earthquake, and then it optimized the design for synthetic spectrum compatible earthquake, almost the same as this one. Yeah. And then it's also when it's optimized the earthquake and it also considering the sensitivity of the analysis. For example, the effect of initial slip load and effective converge and parameter, effective design earthquake. Yep. And for this paper, it's more talking about the slip load, which is the horizontal load. And in this paper, because they use this viscous damper like a bracing, it's talking more about the coefficient damping. Yeah, that's what I understand from these two paper. And here also, it also use the global image and damage index. And finally, you optimize the design solution for the code design spectrum. And it is also using EC8 Eurocode. Yep. So other than just increasing the number of story, I also thinking that if we can try to optimize the design damper for the building, maybe it can be useful. And the last time I tried to optimize the design by only put the damper in the middle, which is we have the maximum displacement in the middle of the building. So if we can dissipate more energy in the middle, we can reduce the displacement and the story drift. But the problem last time, we doesn't get any formula to prove that this procedure can be useful. So I think if we can study good enough with these two paper, and I was thinking this formula can be applied in the in our model.
Yeah, it's not so difficult. But after you find the optimum damper,
Yes.
how do you apply this result to new building? For example, in this case, you have a building and make time history analysis many times to find optimum damping. But so you must do many time history analysis. So it is a little bit time consuming. So in the practical design, you must usually engineer use more simple method like capacity spectrum method. So, well, in my opinion, this research is you can do it. Anyone can do it, but not so useful for practical design.
Okay.
Because you must do many time history analysis.
Yes.
So you must something more. How to implement this result?
Okay.
practical design.
In the displacement-based design method, we also can calculate the equivalent damping.
Yeah.
Right.
Yeah.
I think it was within the displacement design method, maybe we can adjust the damping coefficient from using this formula.
Yeah. Could you show me your paper you submitted for?
Okay.
Well, actually, this paper, how to say, it's not completed, but well, we don't have time, so
Okay.
well, so なんていうのかな、so I hope you should
Okay.
finalize
Okay.
the research. It's not finalized,
Yes.
in my opinion.
Mm.
So when you make a journal paper based
Okay.
on this one, you should improve this paper. So could you go down?
Okay.
Okay, so this is a coupling wall.
Okay.
Yeah. And you have a metallic damper and a viscous damper here.
Uh-huh.
Yeah. So there are three types. The first is metallic damper, and the second is viscous damper, and the third one is a hybrid damper. So it's very interesting. And displacement-based design, you explain the procedure. So the question is not equation 2, 3, 4, 5. Okay. So I don't know. This one is, well, 4 and 5 is somehow theoretical damping.
Yes.
But the 2 and 3 is taken from
Textbooks.
book. So this is something we can do more.
Okay.
Yeah, and could you go down?
Okay.
And this is a design earthquake. Okay, could you go down? Okay, stop. So this is a result with coupling beam without any damper, just steel, right?
Yes.
But actually, this result is very good because estimation of displacement design capacity and the capacity of pushover match quite well, right?
Okay.
And also, so this, how to say, target displacement is designed to satisfy 1/250 story drift, right?
Yes.
150. And this story drift is this dotted line.
Yes.
Right? And actually, the result of time history is also very good matching. Okay? So this is the ideal solution.
Okay.
Yeah, and could you go down? Then you show the result of metallic damper, but unfortunately, it doesn't match. So this is a metallic damper with very strong metallic damper, right?
Yes.
And this is very weak metallic damper.
Yes.
So if you get perfect match result, it means you must increase 150 or something. I don't know. How do you find out? I mean, capacity of metallic damper to match to satisfy this, how to say, this.
The blue line?
Yeah. So
the
this blue line and the orange line, I mean, this capacity must match each other. So this is a procedure of displacement design, right?
Yes.
So, but both result doesn't match. Estimation of design of displacement design is capacity is low.
No, the capacity is higher. The target is low. Means the design is good. That's why the
why? Why it's lower?
Because in the 20%,
Mm.
the damper dissipate more energy compared to 100%. Because in 100%, the damper doesn't yield, but in 20%, the damper or the metallic damper already yield.
But the necessary capacity is different.
What I understand from this graph, like for example, 100%, the blue line actually closer to the how
Yeah,
can I say,
yeah,
the capacity.
yeah.
So the design is acceptable, but the energy
Why
dissipation.
acceptable? It's too conservative.
I say acceptable is based on the story in the story tree.
So how do you design metallic damper too much?
So
How much capacity?
100% same as the metallic the steel beam. So
Yeah.
the
How about
capacity
increasing 150? What will
150.
happen?
Um,
What will-
I haven't tried more than 150 because last time we discussed that we want the metallic damper to be yielding, so that's why we decreased to 20%. So the metallic damper is yielding.
Yeah.
Mm.
So you mean if you increase 150, metallic damper doesn't yield?
Yes,
Mm.
because it's become more stronger.
Mm. Mm. But how did you get this orange line?
From pushover,
Pushover.
1/100.
But why 100% metallic and 20% metallic? Why orange curve is the same? Left one is stronger. So it must be larger compared to 20%. Why these two lines are identical looks?
It's 20%.
So you get this capacity curve and orange curve but pushover.
Yes, 1/100.
And why this orange curve is the same? 100% and 20%.
I'm not sure, but if we compare with, is it because of the damper itself? But if we compare, for example, viscoelastic, 100%
Viscoelastic is
different.
doesn't change because viscoelastic is velocity dependent. So
Mm.
if you do pushover, viscoelastic damper doesn't produce any, resistance. So, I'm talking about metallic damper.
Mm.
Why metallic damper,
I see.
the result of capacity is same?
If we can see, is it because of the damping? The damping is more influenced by the wall compared to the metallic beam, metallic damper itself. This is for 100%, and this one for 20%.
No, I'm talking about static pushover. This orange one. So
Yes.
so equivalent damping is nothing to do with.
So if I try to rerun the analysis, for example, this Stera 3D, and then I put the metallic 100%, so metallic damper.
Spring wall doesn't contribute a lot. Wall is so strong, maybe.
So this one, this is for 20%.
Okay.
Okay. And then I will, so this is 1/100 to the, response structure.
Yeah. Yeah.
20%. This is response structure.
Mm.
So I think it's still the same. And how about if we change? Sure. This is 100%. 290.
Okay. Could you do push over now? Could you
Push over now. Okay.
Yeah, on the screen? Yeah. Oh, coupling beam doesn't yield.
Yeah, this is 100%. If I change,
Hmm.
like it, like it. So I do 20% by 0. Like it's
Oh, it's not yielding. Both result are elastic. Coupling beam is elastic, so that's why the both results are same.
But last time, because it's under earthquake. This is, let me try 5th story, this one. And then, okay, last time, for example, copy. And then member respond.
So it's elastic. Oh, okay.
No, yes.
Could you magnify the picture? I cannot see the color.
Okay.
So it's yielding, but there is no mark on the screen. But it's yielding. Could you magnify up this frame?
This, how can,
Upper picture.
this one?
Yeah, okay.
Okay.
There is no mark here.
Yes.
Okay, I will check Stera 3D. It should be yielding. Okay, so this part should be yellow or red. But okay. So, however, it looks a capacity curve doesn't
Same.
different so much. Not the same, but I mean, shear wall is so strong. So if you do push over, even you change this coupling beam, this result is maybe slightly different, but almost same.
Okay.
So,
If I compare the percentage of energy dissipate for 20% is 2.7, but the wall is a very big damping, and this is for 100%. So for 100%, the damping for metallic is only 0.4. It's very little. maybe that's one of the reason the capacity curve is not much difference.
Yeah. Yeah. How we can,
And Sensei, I have one questions. And Sarah already start doing the 15th story. And then because we increase the number of the story, we check the time history analysis. Actually, 15th story with 500 wall is exceeded the limit. And then we try to increase to 700 thickness, and the story drift can be reduced less than the limit. So if for a 10 story 500 might be too strong, but like is it possible for 15 story if we increase the thickness of the wall, or we should maintain as 500 thickness?
But this coupling wall structure, the lateral resistance is dominated by wall, right?
Yes.
As you can see, also energy is almost dissipated by wall.
Yes.
So we try to design coupling beam, but actually this coupling beam doesn't contribute to not so much. And if you increase thickness of wall, this contribution will be much larger.
I understand. Yeah.
It's how to say, we want to see the なんていうのかな、
The damper dissipate more energy than the wall.
They should contribute to
Yes.
building behavior, but if you increase thickness of wall, this contribution will be smaller.
Okay.
How about the design of
Viscoelastic?
I mean the reference. I forgot the name of the person. I mean, there's a study of coupling wall with viscoelastic damper.
Okay.
And
which only viscoelastic. Is it this one? Is it from Canada?
And in this case, did they discuss about I mean, contribution of wall and coupling beam?
Mostly they just discuss about the damper itself. They doesn't talk about the wall.
Coupling wall ratio is one indicator.
Yes. Degree of coupling.
Yeah. So how much coupling?
But since if talking about degree of coupling is only applicable for normal beam, it doesn't applicable for damper, I think.
Why?
Why? Because last time I tried, but let me try. I think there's in Priestley they discuss about at chapter 11.
It's simple, right?
Yeah, they just times the, for example, the degree of coupling influenced by the beam, and they just multiply the degree of at the for the
Either you apply horizontal force, and in coupling beam you use capacity of coupling beam Q in each story Q, and you calculate なんだっけ overturning moment and shear force. there's a formula.
I remember there's a formula they use to calculate that.
Maybe this is a book of Paul and Priestley.
This is Priestley. The talking about the
There's another book
another book.
we read together in the beginning. And Priestley.
This one.
Yeah.
Design RC.
Yeah, design. Yeah, this one. And they have a definition of the coupling ratio. You should check the chapter of the coupling wall.
I believe it's in chapter 5. Last name, chapter 5. Yeah. Structure wall.
Structure wall.
And then
there must be, could you go down?
this one.
Yeah, there's
system.
かなちょっと待って。そうかな maybe.
6.2. Is around him. And this is what this one.
Okay. And could you go down? Is this what is this? It's a kind of coupling ratio, no?
I think this is coupling ratio because it's divided by total moment overturning. Asian load times the length and then divide by total moment overturning. Degree of coupling.
Yeah, so
here, the case the value A is by moment coupling. Yeah, is
so how much coupling ratio you are?
In my model.
Yeah.
Okay, for example, in the 100%. So for example, this is output from so moments 1 plus moment 2. And then this axial force Q times L.
Well, okay. Maybe.
Yeah, I will calculate later and show you. So in your opinion, for the next we can do to improve the paper is to optimize this distance.
Can I share my screen?
Hi.
So I think you have this paper, optimum degree of coupling for the efficient seismic response of reinforced concrete coupled wall. You have this paper, right?
I
Uh,
don't remember.
I have.
Maybe if I can see the content.
Mhm. Mhm. Mm,
I see this before. Yeah,
yeah, this is he
from
studied
Tokyo University, I
China.
think. Yeah.
Yeah. Yeah. So this is a coupling beam.
Mm-hmm.
Yeah. Coupling beam. Mm. Mm. I think this paper is very nice.
Mm-hmm.
And yeah, this is a kind of ratio, coupling ratio.
Yes.
Yeah. So, and could you compare the, I mean, he also studied some model. And he also applied displacement-based design. This is a picture from Bristol, right?
Yes, yes.
So they are doing almost the same procedure,
Mm-hmm.
but they don't. He doesn't use damper.
Mm.
Yeah, but you should follow his procedure
Okay.
and numerical model and analysis. Yeah, so it's like something like a still 3D.
Mm-hmm.
Yeah. Yeah. And nonlinear time history analysis, earthquake, yeah, and design verification. So he first apply, I don't know, maybe displacement design. I'm not sure. Maybe let's check. 違うかな。one moment. So he also changed, maybe it's a degree of coupling, right?
Yes,
He's
yes.
changing. So in your case, if you change capacity of metallic damper, maybe this coupling ratio change. Probably.
Okay. Mm-hmm.
Probably. Yeah. And he also, yeah, selection of optimal degree of coupling. Hmm. Um, I I don't know if he compares estimation by displacement-based design under time history analysis. I cannot see any comparison. Hmm. But anyway, please read his paper
Okay,
and
yes.
think about what you can apply.
Okay.
Yeah. So I don't recommend to do something else right
Okay, yes.
because your study is not completed.
Okay.
Right? And you are a little bit in a hurry, so I worry you may have some mistake in calculation.
Okay.
Yeah, so it's necessary to uh, examine carefully.
Okay, yes.
OK, so, who is next? Sarah-san, you have something you can show me today?
Yes. Yes, I have. Oh, now I'm gonna talk about metallic of DBDM. And the first, this is under copy wave. It shows wall thickness 500 and 700, and Coleman is 600, and for about as wall thickness 700. column is 800. And from this graph,
sorry, I don't understand. You have a green
okay,
line and yellow line. What is
yes,
500 to 660? What is this? Okay, wall thickness is, column is
yes,
600.
yes,
And 500 is
wall thickness.
wall thickness. And
Mhm.
another, you increase thickness of wall. Okay.
Yes,
Yeah, of course, you increase
and
thickness of wall, the displacement will be smaller. Of course.
yeah,
Mm.
and from this graphic, wall thickness 700 is better than wall thickness
Uh-huh.
500. And from this slide indicate difference of each wall thickness and difference of each column under the cobway. Just only metallic damper. And for about wall thickness 500, metallic 100, wall thickness 500, metallic damper 100% is best one. And for about wall thickness 700, all designs of metallic damper are good. Next slide is this slide also indicate the difference of wall thickness and the difference of column and under the cobway. There's only viscoelastic damper, but unfortunately, for wall thickness 500, all designs of viscoelastic damper are not good. Isn't aren't good, but for about 700 wall thickness, about viscoelastic 500% and the 400% are good. And so this slide is a combination of metallic and the viscoelastic damper. Just only wall thickness 700 column is 800. Before all designs of metallic damper are so good, so I choose 20% and 100% metallic. I choose the metallic 20% and the 100% combined with the good version of viscoelastic damper that was 400% and 500%. And that orange line and blue line is viscoelastic 100. From this picture, viscoelastic 100 is not good. So exclude the viscoelastic 100 combination is not good. It's good. Yeah.
Well, it's interesting. Could you show me slide number 4, previous one? Yeah. So I wonder why, how to say, how can I write comment? I cannot write. Anyway, left one. So if you change the capacity of damper from 100 to 500, the result doesn't change so much. But in the right figure, the result will change, wider. So
Yeah.
why? Thinking about, do you have any idea why you have a big difference in right side, but a small difference in left side? Do you have any?
I guess for about wall thickness 500, common is because this is a different of wall thickness and Coleman and 200, but for about wall thickness 500, this is not too much. I guess before I did a mistake, that was the wall thickness 700, Coleman is 600. And this time I changed the Coleman
Yeah.
to the 800.
But why, in case of large size column and large thickness, right side, why effect of damper is so, I mean, different from 100K and 500K? Well, I have one theory. Zafira-san, do you have any idea why, I mean, the difference of result between damper capacity, right figure is wider compared to left figure?
Probably the 500 thickness is more flexible compared to the 700 thickness. So 700 thickness have more ductility in the wall, and as the coefficient damping of the damper increase, so I think maybe the damper are more likely workable in the 700 thickness compared to 500 thickness.
But why the result is so different in right side? There are five lines,
Yes.
but it's wider.
Yes.
Why?
So Sarah, can you open the coefficient damping for the wall? The
Coefficient of
sev-
damping of
There's a slide showing the coefficient of damping. Can you go slide number 7?
7.
Yeah, this is for 500 thickness, right? So the wall
Yes.
damping is like 12%, and this is for metallic. Do you have for viscoelastic?
I don't have it. It's just the metallic,
Okay.
and this is metallic.
Yes, but we were discussing about viscoelastic, not metallic. Can you compare the wall percentage between 500 and 700? Can you open slide number 7? So here, for under metallic is 12%, almost 13%. How about 700 wall thickness?
Sarah-san, do you have this result for 700?
In this this is
Oh, okay.
Okay, so it's 10%, like 11%. This is for 20%.
Oh, okay. Okay.
This is 100%.
So, okay, Sarah-san, can I share my screen?
Okay.
So, let's see. Can you see my handwriting?
Yes, sir.
Yes? Yes? So my question is why this is wider? This is very narrow, right? So, so, so in this case, wall is 500 thickness, okay? And this is 700. So probably in this case, wall is yielding because it's a little bit, I mean, なんていうのthin. So yielding. And this one is wall is probably almost elastic or yielding is small. So it means damping of wall in this case is very large. I remember it's 12%.
Almost 13%, 12.7,
And this one is
10 point,
Yeah.
10 point something.
and on the other hand, contribution of coupling beam probably larger. This one. And this is probably small. That's why if you combine each other, I mean, contribution of wall is much higher compared to contribution of coupling beam. That's why if you change beam capacity, the result doesn't change so much. However, in the right case, contribution of coupling beam is large. So if you change capacity, the result is, different. Yeah. So if we want to design coupling beam, it's better to use, I mean, なんていうのかな, to make shear wall strong. And we expect energy dissipation by coupling beam. Maybe in this case, it's clear. We can see the big difference by damping coefficient. I mean, なんていうかな。So we want to find the optimum coupling beam, right?
Yes.
So if the result is different each other, we can discuss which one is the optimum.
Yes.
But in left case, the result is too similar each other. So it's not easy to study which one is the optimum. Yeah, so it's a good indication. So, okay, so could you check the paper by Tokyo University,
Okay, sensei.
Tokyo Institute of Technology?
Yeah, Institute Tokyo.
Yeah.
Institute.
And in his design,
Yes.
did he expect yielding of coupling wall, or did he discuss damping of
The beam.
wall and effective damping of beam?
Yeah, I will check, sensei.
Yeah. Could you check each other?
Right, okay.
No. So we must change the model to be this one to be small and this one to be large.
Yes.
Okay, let's continue to study coupling wall structure.
Okay, sensei.
Yeah, I want to finalize this procedure. It's very close to, I mean, なんていうのかな. I think it will be very good study. So
Okay, sensei.
I don't want to stop here.
Okay, sensei.
Okay, so next, Ataya-san is not here today. Majima-kun or Saraya-san, do you have any material to show?
Yes, sensei. Can I present? Can I show my screen?
Okay, okay.
Is my screen is visible, Sensei?
Yeah.
Okay, Sensei. So, Sensei, last time I was discussing about the objective function, where I was reducing the maximum displacement under the maximum considered earthquake hazard, and maximum acceleration under the design basis earthquake hazard, and maximum acceleration under the wind hazard. So I was discussing them individually, how to get the optimum result for those individual hazards. So now I have tried to make one common solution, like for the multi-hazard scenario. How can we define one objective function to get the optimum result of the tune mass damper? So in this case, I have kept the objectives, individual objectives, the same. When you see, I have kept the individual objectives the same. The first objective would be to reduce the maximum displacement under the maximum considered earthquake hazard. The second objective would be to reduce the maximum acceleration under the design basis earthquake hazard. The reason for this is like maximum displacement under the design basis earthquake is very low. So there is no point in decreasing that displacement. But the acceleration, if we decrease the acceleration, then we can improve the comfort levels of the inhabitants even during a small earthquake also. So and similarly for wind, we already know that the acceleration is the problem, not the displacement. So these are the three individual objectives. Now what I have done is I have added those objectives with the weight function, and this weight is actually the frequency of occurrence of that hazard in 100 years of lifetime of the building. So this we already discussed in some earlier meeting on how to calculate the weight. And now because the maximum considered earthquake, this is once in 2500 years, so the weight is very low. And the wind is once in 50 years, so the weight is very high. So so now when I design this tune mass damper with this objective from Bayesian optimization, the result comes that we don't need a TMD for the earthquake, we need a TMD for the wind. Like the mass ratio of TMD for the earthquake is 0.001. So it means like this is the minimum value. So it means that the TMD for the earthquake is not needed. And the reason for that is like one is the weight function is very low, and two is also the displacement under the maximum considered hazard. There could be not like it is not consistently decreased with the addition of the TMD, but the acceleration under the wind and acceleration under DBE also, these are consistently decreased with the increase in the TMD mass. So with this, the result that I have got is like the mean reduction in displacement under the maximum considered hazard is like this, where there is almost 15% increase in the displacement as compared to the unbonded isolators. And for DB, it has reduced a little bit, but not much. For wind, displacement is not so important. But for the acceleration response under wind, the like acceleration has reduced to 14%. So like if it is 100 meter per second square, it has reduced to 14 meter per second square. So the acceleration reduction is very good. And again, for also we have got a 13% reduction in the acceleration under the design basis earthquake as well. But the maximum displacement, it has actually increased than the unbonded isolators. So by addition of this TMD here, the maximum displacement is increasing under the maximum considered earthquake. So next modification which I did is, what if we take equal weight functions for the three objectives? So they are equally important, not based on their frequency of occurrence. So again, I got the result that we don't need a TMD for the earthquake, and this is because like there is not much reduction in the maximum displacement under maximum considered earthquake hazard. So what I did next is I also tried with the like opposite say the opposite weight function. Like this is based on the frequency of occurrence. Now I also tried based on the return period of the occurrence of the hazard. This is not based on any scientific logic, I guess, but I just wanted to try whether it is working. My objective function is reducing fine. So when I use the return period, so now basically the return period of maximum considered earthquake hazard is too much as compared to the others. So now all the TMD is required in the base floor. That is, all the TMD is required to control the earthquake hazard. So, but this is not something which we want. Like, we want to also reduce underwind. So, next step, what I did is I did a slight modification in the objective 1. In objective 1, what I did, objective 2 and 3 are same, like reduction of acceleration under dB and wind. But in objective 1, I checked that if the maximum displacement of the HVC is less than UFREI, then I take the maximum displacement of the HVC. But if it is more than UFREI, I take a very large value of 1000. So what this will do is it will ensure that the maximum displacement is never more than the UFREI. Because if it is very large value 1000, so it will not converge, it will not give you the minimum objective result. So by doing this, I am like neglecting any possibility of increase in the displacement of the base structure under maximum considered earthquake hazard. So this objective will ensure that even if there is not much reduction, there will be no increase also. So for this, I have included this kind of objective. But one problem here with this large value is it is difficult to converge. Like when it tries to fit the Gaussian process and it randomly gets some values of 1000 and then some values of 0.3, it is difficult to get a smooth converged Gaussian process for that. So what is happening is that the estimated and the minimum observed objectives are very different. So the convergence is a problem. So what I did next is I reduced this large value to a comparatively smaller value, say 10. So these are the results with the large value. Again, we see here that the displacement now has reduced. It has reduced from the unbounded isolator case. So now I have taken it as 10. So by using 10, I see that the results are converging very nicely, and also I am getting the required kind of performance from my hybrid controller. Now the results show that we need around 18% of the mass ratio for the earthquake case at the base floor, and the rest for the wind case. So this is kind of some minimum mass ratio that is required tuned to the earthquake, so that the base displacement doesn't exceed the base displacement of only isolated structure. So I think this kind of objective is like well suited for our case when we want to get some practical design where we are not exceeding the isolation base isolation displacement, but we are also getting reduction under wind and earthquake case, under slight earthquake case. So again, here we see that the maximum displacement has reduced, but the reduction in the maximum acceleration is also higher compared to the other cases. So with this kind of objective function, now I moved on to the robust optimization, where I would take some random input variables. So what I did is again, I actually have discussed this earlier with you in a meeting. Like we are considering the maximum mass ratio and the two tuning ratios. The two tuning ratios are one tuned to the for second stiffness of the isolator and another tuned to the first stiffness of the isolator. But the tuning ratios are one, and the time period or the stiffness is different. So both the tuning ratios are one in this case, and we have the maximum mass ratio, which is say 0.1, say the 10% mass ratio of the TMD. So in this case, we are actually getting some samples based on normal distribution and using Latin hypercube sampling. So in Latin hypercube sampling, what this is the function LHS norm. So what they actually do is if can I use it? So say this is a normal distributed variable. So we want some random samples from this variable. So what they do is they divide the sample into various parts, and they take some samples from each part. It is so what happens is, like, if we even with lesser number of samples, we can get very good result, a very good distribution of the variable. So with lesser number of samples, like, we can get a better distribution of the uncertainty. So in this case, we are considering the normal distribution of the different variables MR max and the two tuning frequencies, and the standard deviations of this variable that I have considered from some papers. So it is around, and also from the, I think, Sensei, you gave me the Bridgestone brochure for the variation in the stiffness properties of the isolator. So in that brochure, I saw that the maximum that the maximum variation is around 40% if we consider all the different uncertainties. So with that variation, what I did is, we have the 3 sigma rule. So in the 3 sigma rule, it means that the 99.7% of the um, samples remain within the 3 sigma. So if we consider the maximum variation, say of 40% equals to 3 sigma, so we can find what is the standard deviation sigma, and we can get the distribution of these 3 variables. So with this distribution, now I moved. So what I did is, I have considered these variation in the structural mass, so the mass ratio, maximum mass ratio, and variation, 40% variation in the stiffness from the Bridgestone brochure. So a standard deviation I have received. So this will give me a sample of different combination of mass ratio and tuning ratios for my probabilistic study. So next, so finally, what the objective functions that I have selected is, for the deterministic study, we are reducing these 3 objectives. First is the maximum considered earthquake hazard, displacement, and if it is more than EF area, you are considering 10 value. And second is the maximum acceleration under dB, maximum acceleration under wind. And we are weighting the different objectives based on their frequency of occurrence for a 100-year lifetime structure. In the probabilistic case, Sensei, I actually read some papers, and in some papers there is one method called robust design optimization. So in robust design optimization, what they do is, say, they calculate this minimization, calculate this optimum for 10 different samples of the uncertain parameters. So in this case, the uncertain parameters are this. So not 10, like n different samples. So for n different samples, they calculate this objective function, and they try to reduce. The first one is the mean, and the second one is the standard deviation. So, and this f bar is the mean, and f bar and what they do, they try to reduce the mean and standard deviation according to some weight function. So this weight function could be anything between 0 to 1. So if the weight function is 0, it means that they are only interested in reducing the mean of the objective and not reducing the standard deviation. And if this weight function is 1, they are only interested to reduce the standard deviation and not the mean. So what this signifies is, if you try to reduce the standard deviation, you are increasing the robustness of the design, that your design will always give you similar performance without much variation. And if you're trying to reduce the mean, so the robustness is not guaranteed, but the optimum value would be as such that it will give you the maximum reduction under the given scenario. So say a weighting function of 0.5 would be considering that we also want to reduce the optimum value, and also we want robustness in the region using the different samples. And this f bar star and delta f star, this actually, this is the value when alpha is 0. That is when we are only reducing the mean. So what is the objective value of alpha? This is that. And when we are only reducing the standard deviation, what is the objective value of objective value of the function, this is that. So this is basically normalizing them, because if the mean and standard deviation have very different scales, so just to normalize them and get a objective function which is close to 1, we are doing this. So if we want to minimize this this objective function, we can get a robust optimum design. So now I have planned, like for the probabilistic case, I will reduce this objective function with the alpha value of say 0.5, and denoting that a 50% weightage to the robustness and 50% weightage to the objective itself. And I would use 10 different samples of the different uncertain variables that I have considered. So this is what I have planned. I have developed the codes for the deterministic and probabilistic case. However, for the probabilistic case, I am still running the results. I have not yet received my much results. This is kind of the flow chart that I have developed for the optimization. So for the optimization of the TMD, we already have the optimum UFREI based isolation system. We input that to the simplified HVC control structure, that is a single degree of freedom model with 2 different TMDs. And we have the 3 different excitation scenarios: the maximum considered earthquake, design basis earthquake, and wind excitation. We give them as the input variables. Then initial values of the design variables. The design variables here is the mass ratio of the first TMD, the damping ratio of the first TMD, and the damping ratio of the second TMD. So initial values of the design is input to the structure, and then nonlinear dynamic analysis is conducted to get the 3 objectives. The first objective would be, say, y1 is the maximum of x, where x is the displacement of the mass. Then y2 is maximum of x double dot, whereas x double dot is the acceleration of the mass. And y3, this would be y3, there is some mistake. The y3 would be the maximum of the acceleration under wind. So these are the 3 objectives, and we minimize the final objective with this weight function w1y1 plus w2y2 plus w3y3, where w1, w2, w3 correspond to the frequencies of occurrence. Then a Gaussian process is created evaluating this objective, and if the maximum iteration is reached, then we estimate the optimum values. Otherwise, we go on to estimate the next set of design variables using the acquisition function. This is the basic optimization framework, Bayesian optimization framework, that I have used in the MATLAB program. So with this, for the deterministic case, I have got the results. Say if the total mass ratio is 0.05, I have varied it from 5% to 20% mass ratio of the TMD, the total mass ratio, combined mass ratio. And I have got different values for the mass ratio of the first TMD and second TMD. So I would this is the graph showing the result. So what I have seen is that the damping ratio of the 2 TMDs, they don't show a particular trend for this objective reduction. They are quite random in nature. So this signifies that the damping ratio is the performance is not so sensitive to the damping ratio. However, also I have seen later with the few results that I have got for probabilistic. So if we are trying to make the design robust, the damping ratio are always very high. But if we are trying to only find the optimum for under the deterministic scenario, the damping ratio don't show any particular trend. But a very nice trend is seen in the mass ratio of the TMD. So as the total mass ratio of the TMD increases, this is the mass ratio that is required for the first TMD, that is required for the TMD at the base flow tuned to the earthquake case. So the reason for this is very clear. The reason for this is when we are adding the TMD to the structure, it adds the mass to the structure. So there is obviously some some addition in the base displacement of the structure by the added mass, because now the mass of the structure is added. So the base displacement would be more under the maximum hazard, maximum earthquake case. But when the mass is less, when the mass added is less, then we do not require any mass tuned to the earthquake to reduce the base displacement. But as the mass added goes up, we require more and more mass of the structure to be tuned to the to be tuned to the earthquake stiffness of the isolator to ensure that the base displacement doesn't go beyond the base displacement of the unbonded isolator case. So these are the results so far which I have got. And right now I am working on the probabilistic, finding the probabilistic optimization parameters. So once I do this, I think I can, like, we can write a paper from these results, which I...
Okay. Well, I couldn't follow completely. But could you show me next flow chart?
Yes, sensei.
So
Yes.
I don't know, this one and in previous slide you showed me probabilistic.
Yes, sensei. So
this
yeah.
flow chart is not probabilistic.
No, sensei. This is only deterministic. This will only give us the estimate of the optimum parameters based on this objective function. Now, for probabilistic, this whole Bayesian optimization, this will be conducted, say, for 10 different samples, and then the objective would be the mean and standard deviation of the 10 different samples. So basically the framework could remain same, but it will occur for 10 different cases. So if we are doing, say, 50 simulations in this case, so for one objective run, the probabilistic will actually require 500 simulation for one case for 10 different samples. So, but I also saw some, I also decided that we can also include 50 samples and then randomly correlate them to the earthquake. But I feel this is the most technically correct method to design some probabilistic optimization objective. I was seeing some papers and they don't recommend randomly like changing the samples and giving them to the different excitation. It is better to conduct 10 different simulation and find the mean and standard deviation.
Okay.
So I decided, even if it is taking more time, I think this is more technically correct, so we could include this.
Okay. Okay. Good.
Yes, and sensei also, I want to show the paper for the World Conference on Earthquake Engineering. So the maximum length was 12 and my paper was already reaching 12, but if I reduce the size of the figures a little bit, I could accommodate the 3D model of the building.
That's nice.
Yes, sensei. So now I have added the 3D model of the building with the different dimensions and the TMD locations. And I have explained about this in a little bit in the text. But I couldn't accommodate the design response spectrum. Like there is no much space in the rest of the things. So
yeah. Okay.
Yes. So then, sensei, I will send you this updated version to you now. You can check the updated version.
Okay.
Okay, sensei. Yes.
Okay. 真島くんなんかある？
はい。振動大実験の伝達関数から今、卓越周期を求めようとしてるんですけど、その時に、振幅比に凸凹が激しいので、スペクトルウィンドウを適用しようと思って、今、大崎先生の本を見て勉強してるんですけど、計算の仕方を。その中で、普通にフーリエスペクトル比に対してスペクトルウィンドウをかけるんじゃなくて、フーリエスペクトルからパワースペクトルを求めて、そのパワースペクトルに対してスペクトルウィンドウをかけてるんですけど、パルゼンとか。これってなんでわざわざパワースペクトルに一旦変換してるんですか？ただ二乗してるだけなら、別に符号が変わるわけでもないので。
なんですね。なんか言わん。わかんない。なんだろうね。
なんか本にもただ突然パワースペクトルに対してって書いてあって、なんでわざわざパワースペクトルにするのかが。
理由ないんじゃないの？わかんないけど。
ないです。
理由あるのかな？ちょっとわかんない。
はい。わかりました。もうちょっと勉強してみます。
はい。Okay. So, shall we discuss next meeting? So today is 24. And next week, Saraya-san, we will go to Hamamatsu
Yes.
factory Tuesday.
Yes.
They said you will get the 4,000 yen for, I mean, train ticket.
Yes, Sensei. They have sent me the email also.
Okay.
Yes.
We can do meeting 31st, 1 week later, or 1st of September, Friday. Zafira-san, which date do you prefer? 31st or Thursday or Friday?
Maybe I'm fine with both. Thursday is fine. Thursday. Same day, 31?
Same day, same time?
Yeah.
Okay, 31st to 10 o'clock.
Right.
Okay. Okay, so see you.
Thank you, Sensei.
Bye-bye.
Bye.